2.3, set operations. So when we're looking at sets, we can do a multitude of different types of operations. And the first type of operation that we can do is the intersection of a set. So the intersection of a set so the intersection of sets A and B, written as is a set of elements common to both A and B. And the way that you can write it is as A intersection B is equal to the set X such that X is an element of A and X is an element of B. What does this look like for the Venn diagram? In our Venn diagram, we will have our universal set, and then we will have two sets within here. We will have A and B. Now, A intersection B is simply the elements common to both of them, which is this area right here. So if A contained 1, 2, 3, 4, and B contained 4, 5, 6, 7, A intersection B will simply be 4, because that is the element common to both of them. If both of these sets don't have any elements in common, so say A is equal to 1, 2, 3, and B is equal to 4, 5, 6, then the intersection of these two sets is simply going to be the empty set. And how does that look on the Venn diagram? Well, on our Venn diagram, we have, again, we always have the universal set. And we have both our sets, A and B, and they aren't connected at all, and this is known as a disjoint set. Now we look at the union of both sets. So the union of sets is as follows. The union of sets A and B, written as A union B, is the set of all elements belonging to either A or B. So this is important. It belongs to A or B. How does that look on the Venn diagram? So we have our universal set, as always. we have A, and we have B. Remember how when we looked at the intersection, it was just this part right here? Well, when we're looking at the union between both sets, it's everything in A and everything in B. So if A was 1, 2, 3, 4, and B was 4, 5, 6, 7, then A union B is going to be the set 1, 2, 3, 4, 5, 6, 7. And if you want to write the formula for it, it can be written as A union B is equal to the set X such that X is an element of A, or X is an element of B. When we're talking about the difference of a set, we're looking at the set of all elements belonging to the first set and not the second set. So difference of a set. So the difference of set A and B is written as A minus B, and is a set of all elements belonging to set A and not set B. And not to set B. So A minus B is equal to the set X such that X is an element of A and X is not an element of B. What does this look like on the Venn diagram? So we have our universal set, and we have both our sets A and B. And when we're looking at A minus B, the difference of the set, it's going to be everything in A minus the elements of B. So we're not going to be including this middle part over here, which would be the intersection. We could look at an example of this even further. So we can say that A is equal to 1, 2, 3, 4, 5, 6. B is equal to 2, 3, 6. And if we look at A difference B, A minus B, it would simply be all the elements in A minus the elements from B. So it would be 1, 4, 5. If we're looking at ordered pairs within sets, A, B, A is called the first component. And B is called the second component. And it's important to note that A, B is not equal, it's not the same as BA. And we're talking about ordered pairs because we're going to move on to the Cartesian product of sets. So a set may contain ordered pairs as elements. And if A and B are sets, then each element of A can be paired with each element of B, and the results can be written as ordered pairs. So the set of all such ordered pairs is called the Cartesian product of A and B, which is written as A cross B. And when we're looking at the formula, the Cartesian products of sets A and B is defined as follows. A cross B is equal to the set AB such that A is an element of set A and B is an element of set B. Let's look at an example. So if we have A being the set 1, 5, 9, and B being the set 6, 7, then A cross B would be as follows. It would be the set 1, 6, 1, 7, 5, 6, 5, 7, 9, 6, 9, 7. And that would be our set. If B was listed first, then we would do it as follows. So B cross A would be 6, 1, 6, 5, 6, 9, and then 7, 1, 7, 5, 7, 9. Now, when we want to look at the cardinality of a Cartesian product, the following rules are true. So, if n of A equal to A and n of B is equal to B, then the following is true. N of A cross B is the same as n of B cross A, which is also equal to n of A times n of B, which is also equal to n of B times n of A, which is also equal to AB or BA. Now it's important to note that the Cartesian products A cross B is not the same as B cross A, as we have seen from above. So don't get the cardinality rules confused with the Cartesian product rules. So we could do an example from above where we can go through each thing. So if we look at the cardinality of A cross B, that is going to be 1, 2, 3, 4, 5, 6. And then B cross A would be the same thing. So 1, 2, 3, 4, 5, 6. 6 elements. And then if we look at the cardinality of A, this is going to be 3 times 2, which is going to be 6. And then the same thing for cardinality of B times the cardinality of A, which is also going to be 2 times 3, which is 6. And then it's the same thing as 2 times 3, which is equal to 3 times 2. And the last thing we're going to talk about today is, before we go to De Morgan's law, I'm going to just draw the Venn diagram pictures for each set operation. So the complement of a set is everything that is not within that set within the universal set. So if we have the set of A, the complement of that, which is A prime, is going to be everything else that is not in A. Everything else. Then if we take a look at the intersection between two sets, we have the universal set. The intersection is going to be anything that's common between the both of them. And then we have union, which is elements that is common to either A or B. So anything that is in A and anything that is in B, and I'll do it in a different color here. Then we have the difference of a set. That is going to be the difference of A and B, which is simply going to be anything in A minus anything in B. Now we move on to De Morgan's. De Morgan's law simply states the following. So if we have A intersection B, and we want to get the complement of that, it's simply going to be A complement union B complement. And the same thing for the other way around. So if we have A union B, we want to get the complement of that, the Morgan law states that it's going to be the opposite. So A complement of A intersection complement of B. That's what we have for 2.3.